did, as always, and then I'll get into a little bit more detail on osmotic pressure. I want to remind you, what did I do? Wrote the test, right? I almost wrote the test, so just a reminder of that, okay? Remember, I'm telling you, I did that ahead of time so that I would spoke in. Okay, regardless, last time when it came to colligative properties and dead chem, so we have actually got two backups. Colligative properties are, there's a range of definitions that are in the book. It's really salt water. It's properties of salt water. Let's just cut to the chase. And what's kind of cool about it, so I'm not going to redo all the derivations. I just want to remind you how we started out, because that's where this gets kind of interesting. So remember that if we have a vapor. Now, when I say the word vapor, that means there has to be a liquid. And if we're at equilibrium, then the vapor chemical potential must equal that of the liquid. Now, in this case, this would have to be boiling because that's when a phase transition occurs. And phase transitions occur because the chemical potentials are equal. We covered that before. So if one of the chemical potentials was lower, that would be the dominant phase. Not that there still aren't vapors, and we talked a little bit about that the time before last. Regardless, if they're on equal footing, then you could have either you're at an equilibrium, and so that would be boiling water. Okay, then what we do is we perturb it using Raoult's law. We perturbed it by adding salt to the water. Sorry, I was using the letter B a lot, and I realized that was kind of dumb because B, remember, is our solvent, so that's why I was doing it, but I realized it was kind of stupid. So I decided, since I wanted to stick with just the example of salt water, that's why I kind of changed my notation on the fly. So I'd added, so we're okay, but then I add salt water, and all of a sudden that's there. Remember, this is the mole fraction of water, and remember that all this colligative properties stuff relied on the fact that the solute would not have a big vapor pressure, so we don't mess with this thing, because if it did, that means that the chemical potential changes. Remember that we also said that it's very dilute. Now notice that would be, this would be what? Close to 0? Close to 1. ln1 is, right, so basically, right. So now here's the thing that is funky about this, and I never really quite understood. All right, if we're boiling, this is true, and then I add this, 5 kilojoules per mole is equal to 5 kilojoules per mole plus something. Well, that ain't equal, is it? Yet, hence the limit of this being essentially 1, it is fine. But to the degree that this is not 1, then this equation is just flat out wrong. It's 5 is equal to 5 plus 1, and no, it's not. So that's probably one of the reasons this doesn't really work all that well. Okay, so that's the idea, is to start out with equal set these problems up where the chemical potentials are equal, and then you go from there. So one way to resolve this, remember I said 5 is equal to 5 plus 1, no, it's not, is that the temperature will be different. So it'll fix it, that's the idea. So later what we do is, I realized maybe I could have, there's algebra, there's calculus, there's approximations, and I realized that maybe I didn't do them in the best order. This can be turned into the minus the mole fraction of salt. So natural log of the mole fraction of liquid is 1 minus that of salt. When that number is small, it's just minus the mole fraction of salt. Again, we've reviewed this. And then what I get on the other side is would be the vaporization, H over RT. The vaporization G, vaporization G over RT. Because, per mole. Okay, now the next thing, so actually why don't I bring that negative over here, right? So, okay, so that's all fine and good. And I'm just doing this in a slightly different order than I did last time. Let me point out that what I then do, how do I want to say this? Okay, so the way you figure out the new boiling point is you take the derivative with respect to temperature, yada, 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 gives Helmholtz. And then the next thing you do is you integrate the stuff like this. And that gives you your new boiling temperature. Let me just cut to the answer. God, I'm sorry, I'm not doing such a great job. I didn't really prepare any formal notes for reviewing. I always just kind of look at what I said and try to think of what I meant. Usually I'm not quite this inarticulate. Okay, so anyway, this is what I came up with last time, and I wanted, and this is the new boiling temperature. Okay, what do I want to say about this? I want to point what's kind of funky about this is I have a derivative, split it, and then reintegrate. I've taken a derivative and then I integrate it back. Notice that I had a 1 over t relationship here, taking the derivative and integrating it back. I still got a 1 over t relationship, which, right, why wouldn't I have? That's exactly what should have happened. Let me give a bit of a bigger picture idea of what the heck is happening here. When you take the derivative, this is a slope, right? Right? You've known that. That's probably how you were introduced to derivatives, is that they're slopes. Okay, so what I'm trying to do is I'm trying to map out a relationship between the mole fraction, of course that's still salt. I'm trying to map out a relationship between mole fraction and temperature. So imagine I'm fitting a line, right? So if I'm going to change, imagine I have mole fraction on the x and I have boiling temperature on the y, right? And I want to know what the data is. And I'll fit a line. To fit a line, I need the slope. Right, I need a slope. There it is. That gives me the slope. But now, can I map out the data? No, can I? Do I have enough information to create the line? If I have the slope?
Intercept.
Right, intercept, right? That's only half of this. So basically, what I've got is I've got this general direction, but I don't know where to begin. Okay, this part, remember how we match, you had to do it on your homework? The reason I had you do it on your homework was because of this. You match your starting point. So the mole fraction of salt was originally 0, and of course you're at the boiling point. You're at the normal boiling point of water before you add the salt, right? They match, and then this is then you actually add some salt, so it's not 0, and now you've got T2. And remember, this is delta H over blah, blah, blah. Anyway. Okay, so what this does is, so again, this gives you the slope. When you integrate it with data, you actually give yourself a starting point, which is the same thing as one of you said. And that is the same thing as providing the intercept. And now I can build the line. Now notice that it's not, I'm just using a line as an example. This isn't linear, right? It's not mx, it's m1 over x technically. Anyway, that's just the idea. Idea is trying to build a line, and there's two parts of it. There's a slope, then there's the intercept, which I get here. And that's why this is kind of unsatisfying from a physical chemistry perspective. I would call this a semi-empirical relationship. It's a relationship where I'm using nice ideas of thermodynamics, but it's incomplete, right? I only have half the picture. I have this part, but I don't know where to begin, right? It's a treasure map, but doesn't tell you the starting point, which is useless. So the semi-empirical part is when I insert data to make the model work. So we call those semi-empirical models. So anyway, yeah, there's just that. That's again just a review. And again, I'm not going to go through all the bloody calculus. And then I have to admit, I did paint myself to a corner blabbering about Tuesday about osmotic pressure. And this is the one that's really neat. So I feel bad about not spending enough time on this. I'm just going to take the same, bigger picture look on this. Remember that a point-by-point derivation is in the handout because I really was going way too fast. Remember, there's a couple of handouts, by the way, in case you haven't been following. So remember what happens is, actually, I'm going to draw the process. What we have are these little tubes, and they are connected by a semi-permeable membrane, like a biological membrane. like the membranes in your cells, which are really just incredible things. They're basically soap, and we're actually going to talk a lot about soap after this next test. Soap is actually really what nanotechnology is, so since we're basically done with the formal stuff I need to cover for your MCATs and whatnot, I can spend the last few days talking about whatever I want to, so I'm going to talk about nanotechnology, which is soap. So this semi-permeable membrane can, it's like your cells, phospholipids and all that. Okay, so we're going to fill them with water. So I'll just make sure you know that there's something in there. And I know that the liquid on the, let me draw it underneath so that you know. Okay, so there's the liquid on the left. Now I'm going to leave myself some room. And then there's the liquid on the right. And of course the two sides are even. The liquid is the liquid, so they have the same chemical potential. Why wouldn't they, right? That makes sense. Now, here's what I do. What I do is I add salt. Okay, and notice that I've then perturbed the equilibrium, RTLN. Oh, sorry. I painted myself into a corner. Okay, what I've done is I perturbed the left side. I perturbed its chemical potential. And so, so this equation just doesn't work anymore. It doesn't work because if you're going to add something like this, you're going to have to subtract, you're going to have to balance it out, essentially. You've got to balance it out with something. And, let me make sure I'm looking at this right. And, so we're just, so another way of thinking, the way I put this last time was to say that this chemical potential is not equal to that one, and that was correct. The way I wanted to say it now is I've perturbed it one way, and so I'm going to have to balance that out with something else. Now, that something else, actually, nature does it for me. I just have to understand it. What nature does is, nature abhors a vacuum, and nature abhors a salty solution. And so nature starts pouring water in from the left. Water starts coming in from the left to the right to kind of fight. It's like the Le Chatelier's principle. It's trying to fight the change. And it ends up pressurizing the left half. Now, if it pressurizes the left half, and this is the, that's a column of liquid which has weight, and I can convert that weight to pressure. I mean, that's the definition of pressure. Remember, the pressure is the weight of the atmosphere, which is weird because it's a gas, but anyway. Okay, so what I'm going to do is, I've realized that I've added something on, and remember that this is actually negative, so I'm going to have to add something which is positive to fix it. Okay, so the way to do that is just to remember what delta G is, because we're in a constant pressure temperature world. Okay, so I've got my perturbation, which lowers, remember that's for the liquid, so that's close to 1, but regardless. What I've got to do is think of how delta G changes. And these are chemical potentials, so we have to take everything per mole. Again, a detail that's been coming up a lot, but I will not charge you on that on the test if you forget the per molar. Everything we've been doing is per molar. Okay, and this is, again, is equal to the liquid. Okay, now these chemical potentials are the same. And then as I presented it, I really need to have two different integral signs because they would have different limits. It's not right to have just one integral sign. Okay, so blah, blah, blah. What I did last time was to get rid of this because I said the left and half sides were the same temperature. And again, sorry for my bad use of the board. What I end up with is something that I will not really have on the test, but this is the amount of salt. Okay, so I did a bunch of a couple of steps. It's on the handout. I'm sorry I was rushing last time, but you end up with P equals nRT. I don't see myself actually using this because it's kind of childish. I mean, I'm done with asking you units questions. Also, like when it comes to a freezing point of pressure, boiling point elevation, asking you numerical questions on this is, I'm not really leaning towards that right now. Now, I'll let you know if I change my mind. I'm not leaning towards just throwing this equation at you and giving you numbers and saying, hey, what's the osmotic pressure? I don't really care. That was a first test thing, and we're not there. Yeah, so anyway, again, just big picture of colligative properties, especially as I was going too fast. I do think it's kind of cool, though. I never understood this, like why wouldn't you, I said if this is negative, what you could do is technically cool the solution. So notice that to relieve the stress of this, nature actually has two options. Nature decided to pressurize, this is a negative, so it got rid of it by pressurizing, which is positive. And so it wiped it out, right? And that's where I get the PV equals nRT thing. It could have, now because of that minus sign, it could have, instead of increasing pressure, it could have lowered temperature. The minus sign is doing that, by the way. It could have just lowered temperature, but it doesn't do that. And I remember thinking, well, of course not, because how could the two sides be at different temperature? And I thought, well, temperature is intensive just like pressure. So why not? And I actually don't really understand. I do find it actually intriguing that for the most part when you add salt to water, it does actually get cold. So anyway, but of course it is true that unless you are actively cooling or heating just one side and insulate the other, it is true that this will not be true in that anyway. Blah, blah, blah. So it's all sensitive. Okay, so again, I just wanted this normal review, and I just wanted to take a little bit of a bigger picture and explain a little bit more about why this part here works the way it does, because I do find it a little funky to take a derivative and just reintegrate it, but hopefully, hopefully I'm right about that. I think I'm right about that, and that makes it a little bit clearer about how all this works. And again, a little bit more test taking hints. Your homework where you do the calculations, which are recycled questions. I don't have many good ways of changing those questions. Those questions are the kind of thing I like to put on homework so that I won't put them on the test, because they're calculator questions and you needed to use Mathematica to solve most of the questions, and you should not be whipping out your computer in the test. So I am not leaning towards any of those on the test, but remember those questions outside of that, yeah, very much so. Okay, so we're done with chemical potential of gas equals chemical potential of liquid. We're done with Henry's law, Raoult's law. Remember that when it came to the thing I just deleted, that was a Raoult's law, which is wrong, right? But anyway, so we're done with that stuff. Now we're going to get into his phase diagrams. So let me write that down. Phase diagrams. Now, this is a little bit more detailed information that I unfortunately, again, I'm not going to be doing a lot of derivations. The derivations are very simple, which is great. This is more graphical, it's more visual. So for you graph people, I have graphs on the exam for you. While this is one of those things, again, I don't like the third part of this class. This is more stuff to remember. It's really, really easy. So that's why I want to go forth on this and put it on the test. And one thing I don't have on the test, but I have on, I think I put this on your last homework. What are you on? You're on homework what? Oh, okay. Well, if I do anything more, this will be on homework 11, the fake one, or the one that you won't actually have to turn in. Anyway, now remember, I showed you this last time, and if I ask you like what happens when you add salt to water, you just whip this out. You kind of need to know this for what we're covering right now with your phase diagrams. And anyway, I could put this at you and then say, hey, fill it out, and you should remember that at high pressure, low temperature, of course you're going to have a solid. And if you're at high temperature, low pressure, of course you have a gas. And that leaves the liquid. Actually, I should put this here, because as I drew a little bit last time, there's this weirdness, which is the critical phase, which lies outside of the liquid or gas. And the critical phase, now you've all heard of supercritical liquids, supercritical gases. Those are the same thing. It's just kind of more, if you're a liquid and you pressurize it, which is really hard to do, but if you pressurize something to the critical phase, we tend to call it a critical liquid. If we have a gas and we heat it up to the critical phase, we tend to call it a critical gas, but it's the same phase. My point being is that that's not meaningful. It's all just the critical phase. And it is its own phase. And I'm not going to say too much about this. I guess if we go to higher temperature and pressure, we get to plasmas, and I don't think there's anything beyond plasmas because the atoms are broken down. I'm not going to talk about plasmas. But I do want to say that the critical phase is its own phase. And that's because that, just like solids and liquids are just by visually very different, critical is very different because things like, I know like CO2, critical CO2 is as good a solvent as water. Actually, so is xenon. If you can get xenon, liquid xenon to the critical phase, it will dissolve dirt in your clothes as good as water does. In fact, when I was in North Carolina, one of the faculty there that I worked with sometimes, Joe DeSimone, who's wealthy beyond words now, he actually figured out that you could use CO2, supercritical CO2, to do dry cleaning. Because right now, they do dry cleaning with, was it dichloro, does anyone remember dichloroethane, something like that? Anyway, they used an organic solvent, and I tell you, people always complain that they can smell it, but do this. Has any of you ever cleaned a comforter, dry cleaned a comforter? Yeah. Yes, no? Yeah, what happened? Did any of you? No? Okay, so I've dry cleaned my comforter. Oh my God. When I took it home, I just had to leave it outside because of the smell of the chemical. So what happened was that the guy I used to work with in North Carolina, he actually ended up making a company where they got CO2, supercritical CO2, and used it as a dry cleaning device, essentially. Of course, the idea is it's environmentally friendly. The problem is that the critical phase is like really dangerous. Now remember, I've been telling you, pressure, high pressure, high temperature, super dangerous, and so is this. So it didn't take off. So anyway, blah, blah, blah about the supercritical. Let me point out, let's see. Another interesting thing is right here. As I walk you through what all this means, this is the triple point. And that is where all three phases are equilibrium. Also, I want to point out, this is also a single component. So this is just water. Actually, I've drawn a very water-like. You'll understand that fully by the next hour. This is a water-like phase diagram, so this is just for one thing. We're going to cover what happens if you add water and ethanol, how it changes. We're going to cover that in a little bit. So this is what happens when we have all three phases together. And so as I also mentioned, here, let me redraw this, and let me do one of those times. I know this is kind of awful, but let me draw one with some degree of modicum of accuracy. Again, I'm going to do water. So, let me do water here so I can point out some other features. There's a lot more in here than just solid, liquid, gas, so triple points, critical points. Remember that if you're on a line, the lines are really the most important thing here. If you're on a line, then that technically means you have liquid and gas in equilibrium, which is really kind of difficult to do. Imagine like if you have, it's like right, any of these points here, it's like you've got a kettle boiling and it's in a metal box such that what you would see is if you could look inside of it, because I've seen this done actually, is so imagine you have like a metal box in a window and you have boiling water at equilibrium with the gas. What does that mean? It means that actually with just say a little bit of heat, the liquid would just disappear and turn into a gas, just kind of at almost like a whim. Cool it just the tiniest bit, delta T, then all of a sudden all the gas would turn to a liquid just in the blink of an eye. So that's what that means to be at equilibrium, and it's really not all that easy to be truly on one of those lines. Anyway, blah, blah, blah. So now let me give you the phase diagram of water with some accuracy. Here is the melting point, here is the boiling, so that's room temperature, the boiling point is 373, and here is pressure. And, okay, so here's the triple point, and this is just slightly above 600. This will be in pascals. It's slightly above that. Okay, then I need to have a break in the graph, and of course now I need to have 1 APM. Okay, so there's 1 APM, and this does like this, and this goes like this does like that. Okay. Okay, 273. Okay, so we're like right here. And okay, room temperature, 1 atmospheric pressure. I'm in the liquid region. And again, here's gas and here's the solid. It's not hard to figure out. I'd actually pointed this out to you that what you can, sorry. I didn't draw the graph right. So what you can read off this thing is that if, as much as you're a liquid, you can read off what your boiling point is. Your boiling point is at 373, as long as you're at the right pressure. Notice that if you go high up into the atmosphere, you can also see, climb a mountain, right? You can see that your boiling points decrease, which is why you add salt. Remember, I brought that up two classes ago. Now remember that also, despite the fact that you're in the liquid region, sorry, this little is bothering me, sweet thing. So, despite the fact that you're in the liquid region, you know that there's still a vapor. The vapor is still present, and you can read off its pressure. Now, when I said before, I remember I was always saying that 600 pascals is the vapor pressure of water. That's at 0 degrees. At 298, it's actually right. It's on your homework, right? I don't know if you noticed that, but you're actually solving for this on your homework. At room temperature, it's higher than at 0 degrees. It's actually a lot higher. I think you're supposed to calculate around 3,000 pascals. So notice that the y-axis is really steep, right? Okay, so just a hint there. And if you did it at 0 degrees, then you would get a little over 600, 611 pascals. Anyway, I'm just getting the answers. Okay, question.
You said if we add salt, the boiling point will go down or up?
It will, now, all right, so, okay, I was talking about what happens if you climb a mountain. So we go to lower pressure, in which case the boiling point of your liquid goes down. And so that's why if you live in Denver or Mexico City, you have to cook things longer because you're at a lower temperature. So one of the solutions is to add salt. Remember, boiling point elevation. So I'm just trying to remind you that when we started talking about derivative properties, that's how I introduced it. And remember, I got really confused for a couple of minutes, and that's because of this. Lowering pressure drives you down, adding salt drives you up, and I got confused. That's why I stammered a little bit that day, which is on video and will forever be on video, which sucks. Actually, before this class, I wanted to try to make sure I nailed it because this is the last time I'm going to videotape. Okay, so last thing I wanted to point out was a little bit more about, again, let's be at room temperature and pressure, and let's think a little bit more about what it means to be a liquid when you know that there's gas. And so, I used to bring a demo. I used to bring a demo about what it means to be on this point of the phase diagram and talk about gases and liquids when you're obviously in the liquid region. And what I would do is I'd take a cup of water, I'd bring a clear cup, a nice glass thing, clear, and I'd bring a cup of water and I'd pour it in, and then I would just stand there for like 20 minutes. It was really awkward. That's why I stopped doing it. But you know what's going to happen, right? It evaporates. Okay, so tell me this. Why am I on the liquid phase diagram? And it's all going to evaporate. Why am I on the liquid region if all my liquid turns to gas? Why am I there? I mean, clearly, and you're right, no trick. I mean, you know that, right? If you leave out a cup of water, it gets nasty, but it's okay because it evaporates. So why am I in the liquid region? how can anything evaporate to begin with, right, if you're in the liquid region? Something you've taken for granted since you were young, but yet you know liquids evaporate up there. The gas dissipates, but now, okay, and that's correct. If you put it in a box, you would actually reach an equilibrium. Assuming that our atmosphere had no water, okay, that's a little weird, but whatever. So, and I have a cup of water and I put it in the metal box, the vapor pressure would rise to this point right here. Again, I think it's 3,000 pascals, and then it would stop. The liquid would no longer evaporate. But why does it evaporate to begin with? So that's what I'm actually confusing. Why would it evaporate to begin with? Again, if you're in the liquid region. Yeah? What is that? Any ideas? This is a graduate level question, by the way. Well, take a stab. Why not?
Yeah. The bonds will be weaker
On the top?
on the top.
That's a good way of thinking because, yeah, that's where we want to start because that's where the vapor comes from. Just like when I was mentioning Henry's law, why Henry's law might be larger or smaller than the pure vapor pressure, because you got to think of the surface. There's a little bit more to it than that, and again, this is actually graduate level, and we're actually going to touch on it a little bit in 344. This is what I do in the first week, and don't write this down. I'm always prepping for 344, but the first thing we're going to do in 344 is we're going to calculate the probability of a gas molecule having a certain velocity. And what you're going to find is that for, O2 gas at room temperature and pressure, you're going to derive a curve that kind of looks like this. It's a skewed bell-shaped curve. And so what you see is that some are cold and some are hot. Okay, my point being is that as much as I can have a balloon full of O2, it's at room temperature and pressure, and I can know the energy, I can know its U and calculate its speed. Who believes that all the molecules are at the same speed? That everyone is moving at exactly the same velocity? Does that sound unrealistic? Yeah. And it should be, because I just drew for you what the heck is actually happening. Some are not moving at all, and some are moving at almost the speed of light. Well, that's an exaggeration. Some are hot, and that's the same thing as being cold. Okay, now, so when it comes to a bucket of water, let me get a new board. When it comes to our bucket of water, the same thing is happening. There are molecules, and they're at the surface, some of which are hot and some of which are cold, because there's these natural fluctuations that occur. And again, this is the kind of thing we do cover in grad school. And we do this with equations, by the way, that take 10 years to solve, or more accurately, about 20 hours. When you go to grad school, we will give you homework sets that will take 10 to 20 hours. But remember, we actually we pay you to do it. So it's not that big a deal. We can be abusive if we're going to pay you. So, okay, I've got water molecules on the surface, and the way to think about this is that they're moving around, and they're moving around on this kind of the small couple of molecule scale. That's the right scale to think about this. And what can happen is that a couple of them decide to smash into this guy. They don't like it. They don't like this one. They all happen to just kind of give it a whack. And that caused it to eject. Eject right out of, oh, that's awful. That's the OCD kicking in. They caused it to eject right out of the solution. And then it, of course, as was mentioned, it actually walks away if it wasn't kept in a metal box. So that's why it all evaporates. Okay, now, what happens to the temperature of the cup of water? All right, we have one vote for same.
Wouldn't it decrease?
It would decrease. It would decrease, right? Because if it stayed the same, it would basically have the same energy. Same U, right? Because U is proportional to temperature, yet you lost a hot molecule. That molecule had more temperature than it should have because of these like less than 1 nanometer scale fluctuations that occur. And that's, again, things are chaotic. That's entropy for you. So yeah, this got cold. When this process happened, it got cold. So why doesn't it freeze? You know this happens until the whole freaking water's gone. So why doesn't it freeze?
Just the molecules moving around.
They're moving around because they have temperature, but they're losing it. My point is that this can only go on so long before it freezes. Surroundings, right. Technically, it's the sun. The sun does it. And that's why we have everything on this planet, because of the sun. And remember, the reason we have oil and coal is because of the Carboniferous time, eon or epoch or whatever, when we had way too much oxygen. It was like 30% oxygen. Forests grew like mad. Microbes didn't digest wood like they do now, so all that plant material got compacted into the ground, so we get coal and oil. So when we burn coal and oil, we're burning, I forgot how long, 100 million years, this, eons, they last like 100 million years. We're burning 100 million years of solar energy stored into all that, those dead trees. Anyway, what else did I want to say about that? I think I had one more point. So let me tell you what's happening when something boils, and let me redraw the pressure, temperature phase diagram. And so I hope you do get kind of used to this. Okay, what happens when, let's take a cup of liquid and let's put it in a microwave, and we're slowly heating it up, right, at constant pressure. So this is a cup of water in a microwave. What's happening is, as you really get, especially as you get close to the liquid vapor line, liquid gas line, this process is occurring more and more, and it starts to occur inside of it. So on these 1 nanometer scale, I'm not trying to draw oxygen, just kind of forget about all this. What's happening is you're getting these bubbles of gas. These bubbles of gas are forming as you increase the temperature. And little fluctuations, just like I mentioned, little fluctuations, but now they're occurring inside. Little gas bubble forms and it just collapses. And again, these are like a nanometer. You don't see them, right? I'm not talking about the bubbles that form on the side. These are all happening on the inside. And as you get closer and closer, something really curious happens. This is something, again, I learned in grad school, is that you get more of these bubbles, but a cool thing happens is that they're correlated. It means that if one forms here, there's going to be another one that's not that far away. It has to be there. And of course, if that's there, then there has to be another one that's not that far away. And of course, you go on and on and on. Now, these correlations increase as you go further and further, as you're really getting close to that line. But of course, once it's perfect, then everything's a gas, right? So there you go. And that's, of course, when you're seeing, when you see bubbles along the sides, because there's a jagged edge. We're going to talk a little bit about edges. And so those are just nucleation sites. Actually, one thing that's kind of neat is, another thing, last bit about phase diagrams, is that these are equilibrium phase diagrams. You can actually put liquids, let's do liquids. You can put liquids into regions of instability as long as you don't do it, as long as you do it transiently. Okay, so what does all that mean? That's a lot of graduate level language. What it means is that my mother, one time I was coming home from college, and I heard my mother scream from the kitchen, which, a guy, right, that makes me jump at an unbelievable level. So my mother's screaming, I run into the kitchen. What happened was my mother had a cup in the microwave, microwaved it like normal, like 3 minutes, and it wasn't boiling. She thought the microwave was broken, but so she got a spoon and then touched the liquid. So what happened?
Water jumped.
Right, it exploded. Any of you ever have that happen? Any of you? You have, yeah. There's always at least one person who's seen that before. You can, as long as you're not in equilibrium, you can actually go past the line and have a liquid in the gas region. Now, it's not going to last. That's not equilibrium. And as soon as a jagged edge forms up, it'll nucleate and it'll go off all at once. I mean, this is really dangerous. I'm kind of surprised that actually it's usually more than one person has seen this happen before. This is also why coffee cups, they're not smooth. You should never produce, manufacturers do not produce smooth coffee cups because this would happen a lot. So they don't do that on purpose. Another thing I can tell you is, I got the numbers here somewhere. This goes the other way. There was the record was, what happened was, these people at Berkeley, they got a stream of, they got this source of water, and then they pressurized it through a little nozzle, and it went into a vacuum. And just like a breeze cools you down, when the liquid jet went to the vacuum and it evaporated, it cooled it. It remained a liquid as it shot into the vacuum, but the temperature got down to minus 63 before it formed ice crystals. So that's an example of sometimes we just do things for the hell of it, but that's the record on cooling a liquid into the solid region, and that's as far as they were able to push it. I actually was in the room when they did it, by the way. That was kind of cool. I was just visiting a friend, and he said, hey, we just get minus 63. And I'm like, hey, what does that mean? It means this. You don't care, do you? So anyway, Kevin Wilson, he actually still works at the Advanced Life Sources at Berkeley, who actually did that experiment. I think he still holds the record. Okay, so last bit are, I want to actually describe, there are rules for when you have, I would call this an open plane. I would call this on a line. I would call this on a triple point. There are rules that define when you have open planes, lines, or triple points, and that's called Gibbs phase rule. So I'll start here. Gibbs phase rule. Okay. Write that down. You guys could have figured it out. Nadia's dad was more interesting. Regardless, they're all dead. Okay, so the whole point of this is you define degrees of freedom. And so degree of freedom, this is not what we covered last time. This is not rotation, this is not vibration, this is not translation. In the case of, let me wipe this out and just do it again systematically. That's kind of a mess. What I mean by a degree of freedom, so don't get confused when I ask about this on the test with degrees of freedom like we talked about when we covered U. A point here, this is a single phase region because it has 2 degrees of freedom. So I'll just write DOF, 2 degrees of freedom. Now what that means is that I can still change pressure and temperature and still retain so this is a gas. I can change temperature and pressure and there's still a gas. That's the idea. That means 2 degrees of freedom. If I'm here, I actually have 1 degree of freedom. Okay. What that means is that if I exercise my degree of freedom, let's say I heated it, if I want to retain a simultaneous liquid-gas equilibrium, I'm going to have to change the pressure. I'll have to increase it. So again, it's fairly straightforward. For some reason, I need to maintain an equilibrium of gas and liquid, and why would I ever do that? Because I'm doing some kind of chemical reaction that requires it. That's why, by the way. So I need to maintain liquid gas. I've decided to increase the temperature, but if I don't monkey with the pressure, I'm going to lose it. I'm going to basically form a gas, all gas. So if I want to keep the liquid, I have to increase the pressure. If I increase it too much, then I get all liquid. All right. So the reason 1 degree of freedom is that if you change temperature, you have to change the pressure. Change the pressure. I don't know what's wrong with it. Change the pressure by an exact amount. You don't get to choose. If you're going to go up, 5 degrees, this way, then you're going to have to go up 5 pascals. It's defined for you. No option. And of course, the triple point is obvious. If you're here, you have 0 degrees of freedom. If you perturb any factor, you will not have both liquid, solid, and gas present in the crazy metal plots that you do these. I'll actually post a YouTube video. I have 2 YouTube videos. I'll just link them. I'd be probably copyright infringement if I just downloaded them. But so I have two YouTube videos of showing what a triple point looks like. It's really this chaotic mess. It's kind of cool. And I also have another YouTube video of what it looks like inside of a metal box with a window at a critical point. Okay, so tell you what, why don't we take a break there? And yeah, this is a good break. What I'm going to do is I'm going to come up with a formula that's going to give us these numbers 2, 1, and 0. So I've got a formula. I'm going to derive it in the next hour. for what gives us these numbers of degrees of freedom. And then the next thing I'm going to do is I'm going to come up with an equation that actually tells us exactly what these points are. And I do have that on the test, by the way. So, and by the way, it's very similar to what we just did for colligative properties. It's this relationship I'm going to derive called the Clausius-Clapeyron equation. Don't worry about it, it's in the next hour. And I'm going to take like the derivative and then reintegrate it. So the derivative tells me how I travel along the line, but then I'm going to have to use like a triple point to establish a starting point. So that's in the next hour. So anyway, all right, 10-minute break.